Hi guys, it's me, Ziwi. If you are as creative and as one in a generation kind of mind as me, you probably at least once in your life wondered if you could beat the casino and all the gambling systems. And I've thought about it for a few days and decided if I'm not smart enough, why not just try and train a system more intelligent than me to try and predict the outcomes.
One of the more unpredictable gambling games is, of course, the slot machine. It is widely known that the slot machines are one of the gambling systems where the house almost always wins and where the odds are always against your favor. Nothing you do influences how the slot machine will play.
But what if I tried to train a machine learning system to learn patterns from the data of my slot machine that I created right behind me? Before we start and I show you this simple program I wrote, I want to talk about why I even at first thought this was possible to do. For the general public who isn't really concerned with how computers work, the algorithm or a pattern in which the slot machines pick their symbols, even if they are digital or if they are mechanical, may seem completely arbitrary at first hand. But if you're familiar with some computer science topics, you may already know that generation of completely random variables and numbers is one of the most famous unsolved problems in computer science today. The computer you cannot just generate a random number out of nothing. So this is why I at first thought it even may be possible to just try and train an intelligent system to learn patterns from the data and try to somehow reverse engineer and break the algorithm that would create these random numbers. And I would first like to take a look at how random numbers are generated in a computer. So how do we create and arrive at a number that would look just randomly generated, at least at first sight?
So programs and algorithms that are concerned with
producing random numbers or pseudo-random numbers are called random number generators.
And I would just like to add pseudo, because they try to model this behavior of creating random variables, but as you will see, they fail to do so. One of the most famous computational methods is just the linear congruential generator. And the number that we'll mark by xn plus 1, which is the newly generated number, is defined as a, where a is some constant, xn plus b, and we won't look too deep into picking just the constants and variables of a, b, and m, so that the generation of numbers is adequate for us. But the one thing we are interested in is just looking that it is defined recursively. So we just pick the first starting point, also called the seed, of x0, and we generate all the next numbers from a previous one. Some random number generators also use numbers not from directly the previous iteration, but a few iterations before that one. This would seem to us that if we let a machine learning or an AI system to just learn the patterns for a long enough time and on enough data, it would in theory work, right? Because it would pick out a sequence of numbers that would start at one point repeating itself. But this is where the catch is. The period of RNGs is extremely large. And I just want to test it out for myself. If we can pick out a certain sequence with two different approaches that are not so computationally intense and try to apply them on our simple slot machine program. All right, we are now in my Visual Studio program, and I just want to take you on a quick guide of what I've done here, and you don't need any coding knowledge to understand all of this. I will explain it to you not so much in depth, but just so you have a general idea of how this program works. Here is just the simple 30-line HTML document that is just the structure of our visual representation of the program. This CSS code is just the styles and the colors and everything I've done. So the program and this experiment looks more presentable and and watchable for you. And this is the slot logic. It's just the 100 lines of code that I'll explain to you when I open my program. So here is the complete program. It is of course running at my local host, and it is of course called the ZWiz Ultra Jackpot. And unlike real slot machines, ZWiz Ultra Jackpot doesn't waste your real money, just your dignity, self-respect and time. And how this program works is we just spin the slot machine a few times, and we have a starting balance of $150. We can just spin the machine without investing anything, just like this a few times, and get a certain result. We don't lose anything if we don't bet anything. We can just spin it forever if you want. But I'll just run a quick simulation and I'll try and beat the machine on my own, just inserting and creating some bets if I feel like I'm going to win this spin or not. Before I start, just to explain the logic, there are 7 symbols. There are cherries, watermelons, diamonds, robots, pythons, poops, and lucky 7s. The workings of ZWiz Ultra Jackpot is created so that if you get 3 same symbols, you win a prize or you lose more money than you bet. If you get 3 poops, you lose 20 times the amount of money you invested. If you win 3 robots, 3 pythons, 3 watermelons or 3 cherries, you get 10% of the bet you invested. If you get 3 diamonds, you get 20 times the bet that you put on, and if you get 3 P7s, that's a jackpot, and you win 30 times the amount that you invested. This is also captured here in the logic of the function spin. So we create a spin, we pick from a switch what we've got. If you understand code, you can take a look right here, and here we have a logic for the losses and wins, updating and putting out the balance. We are listening for every spin, and that will be about it. So I'll just run a program a few times and see how well I do. Alright, so I lost almost everything. I won't play after this one. So you now may be wondering, how would the artificially intelligent system do in this kind of environment? And that's what we are talking about right now. Because I was using the JavaScript's internal random number generator, or the included random number generator. So to be completely fair with the artificial intelligence systems or the machine learning models we are going to use, I will export with this function. As you can see, I already exported the spins from this function right here, so we can use it in our Python models that I created. This way we won't use 2 different random number generators. This wouldn't make much of a difference, but I want to be completely clear that the JavaScript's random number generator also generated the data that we are going to train our models on and that our models are going to learn from. So here is the training set. It has around 1000 inputs. I think that's not so much in terms of modern artificially intelligent machine learning systems. And we can see that these are the inputs. We will represent them as symbols later. It's just so the computation is a lot simpler. I represented them as numbers again, like they are represented in our original program as well. So if we go and try to search for ones, let's skip to the last item. We can see there were a few wins on this training data. So our model should be able to pick from this pattern of data at least some kind of recurrence. And here are the Python models. This is just a list of emojis, like a map, that is going to represent them in a way they were represented also in the program. And of course, our goal is to model the randomness of the random number generator with these 2 models. The first one, here we just import the data from the file I created, and here we have the logistic regression. It is one of the simplest machine learning models for the classification. Before we start, I just want to explain to you in layman's terms and quickly what we are trying to do. The logistic regression and why we are using it. Instead of trying to just predict the output after a certain sequence of spins in terms of the symbols, it would be a lot easier to just model if we won or not. So instead of trying to guess if there are going to be, I don't know, 3 cherries, or if there's going to be 1 watermelon and 1 cherry and, I don't know, 1 snake, we just try to predict if the next spin after this one is going to be a win or not. And we can do that from the training data. We have a training set of certain number of spins. In our case, it is 1,000 spins. And we also have if those spins were winning or not, in our case. So just try and imagine that we have a huge list of spins where each spin has 3 different symbols. So this is the first spin, this is the second spin, and we know what those symbols in those spins were, and we have 1,000 of them. In the other list, that is one-dimensional, this is a 2-dimensional list because we have 1,000 inputs in our list, in which all the inputs have 3 different symbols. So it is called in computer science a 2-dimensional array. And our other list, this is a list of spins. We have if they were winning or not. So 1, 0, 0, 0, 0, 0, and so on 1,000 times. And if we trained our model to correlate this spin, whether it was winning or not, we would train our model to, without knowing the rules, try to guess which combinations are winning and which are not. And we don't want to do that. We don't want to model the current spins because we already know which ones are winning and which are not. We want to see if this, for example, this spin right here correlates with the third input, creates the win in a third spin. And that's what we are trying to model. We don't want to compare them side by side from the same iteration. For example, the second spin and the second result. We want to train our model on ith spin and how they correlate to the I plus 1 result. So what we're basically saying is that we have to take the second array of our results and shift them 1 space to the left. That way we see from the current inputs if the next spin is going to be a win or not. Because for this spin, which is second in a row, the third result in a row is what happens after it. And that's what we want to teach our machine learning model to predict. And the logistic regression, the only thing that it does is that it tries to separate the winning results from the not winning results. And we do classification because we only have a binary number of results. We either have a win after a certain spin or not. One thing I also want to mention is that we are starting off with trying to predict the result from just the previous spin. So we don't take into account some number of previous spins, but just the previous one. And how would logistic regression look geometrically in our certain case? Well, let's examine a third-dimensional space defined by 3 coordinates. And let's say this is, for each spin, this is our x1, this is our x2, and this is our x3. So for each spin, for example, cherry, again, watermelon, and I don't know, a cherry again, we represent those symbols as numbers. In this case, it is 1, 2, 1. And we try in this 3-dimensional space to create how exactly does this combination look. And for example, our cherry would be 1, our watermelon would be 2, and it would be again 1 in height. in this case. And this dot would represent our spin. We represent the losing ones as green, and there will be many of green ones all around our space, because there are a lot more losses than wins in our scenario and our machine. And somewhere here, there exists a blue one that is a win. And what the logistic regression tries to do is that it tries to separate these results with a simple plane. And as you can see, our wins get lost in the noise. And we cannot just associate certain spins with certain wins, because one time one spin could lead to the next one being a loss, and the other time it could be leading to the next one being a win. So there may be even cases where there are the same spins that point to the same point, that point to different results. One is green, one is blue. And we cannot drive a plane here and try to separate those. It is impossible. And we'll see how our model performs right now. So let's take a look once again at our model. We shift the array, we leave a space. This could be done a lot more dynamically, but I was stupid and I statically defined what points in our dataset I want to test it on, but it doesn't matter. And you can see here that what I've done is that I separated the data to the training and the testing set. So all of the data is separated. At least approximately 90% of our data goes into training and 10% goes into testing. And I disabled the shuffle just so because we'll see later that we don't want our testing data to enter in our training data. That way the model would create biases. Are fitting the model and training it on logistic regression, and we try to predict and test our accuracy score against the real results. And here is testing the model on the previously unseen data part, one by one, and I'll run the model and it will create files right beside here, and we'll take a look at what it was actually doing. Our betting strategy is quite simple. We predict if the next result is going to be more likely a win or a loss, and we don't create a safety margin to try and separate. So we just gamble the money if we think it's going to be a win, doesn't matter and what the confidence of our model was. And I also simplified a lot of the logic here. If there is a match, the model is always going to get a 30 times its bet in return. So it has a lot better chances than me to gain a lot of money. In every other case, we subtract the bet from our budget and we write a budget. And I'll just start the model right now and we'll take a look at our logistic regression. And what you can see right now is indeed really interesting. Because the wins are so rare and they are lost in extremely large noise, our model decided to, because I allowed it to place bets of 0 like I could when I tested it, it decided not to become a gambler, but instead to become a philosopher. And this simple model could in fact teach us a lot. So these simple linear dependencies that of course even a human could recognize if one spin was leading to the next one being a win, found 0 patterns and decided that the best strategy almost all of the time is just to, as you can see, put bets of $0 and not bet anything, anytime. Prediction is what will happen after our input spin. Actual is what indeed happens. As you can see here, this is our next spin, and the budget didn't change at all. The model accuracy is pretty misleading because it just doesn't gamble and plays on losses all the time. And predicting a loss in a slot machine is like a meteorologist having a 90% accuracy predicting that there is not going to be any rain in the Atacama Desert each and every day. And of course, the model is right. But what we are more concerned about is the accuracy on our wins. Did it, because we allowed it to not place any bets when it thinks it's going to be a loss, did it predict any wins? And there was just one win in these 100 examples. As you can see, these 3 cherries. And before it arrived, the previous spin was 2 snakes and a poop. And it was 89.4% confident it is going to be a loss. So it just cannot predict in any way what is going to happen after a single spin. So the real accuracy we are concerned about in this model is not going to be 89%, it's going to be 0%, much more close to the results from my university math exams. But we are not going to give up, at least not yet. And we'll take a look at our second kind of model, which is the simple feed-forward multi-layer perceptron neural network. It is loosely inspired by the way the neurons are connected in a human brain. It is a subfield of specifically deep learning. And what deep learning allows us is to model a lot more complex relationships in a system. I was thinking about jumping to random forests now, but we already can conclude that just the simple decisions based on our previous examples would lead to no results. So we jump to a more complex structure. How do they loosely work is that they have a certain number of inputs. In our case, it would be 3, because each of our spins has 3 symbols. And this is the input layer. And right here in between, we have a few number of hidden layers. And they are all interconnected.
At the end, we have just 2 simple neurons, and each this neuron represents a function. Output ones are 0 and 1. If the neural network thinks that this sequence we provided is going to lead to a win or not. But we already know that even if this is a more complex system, it cannot truly learn from just 1 spin and 3 previous symbols. So we try, and because I was using scikit-learn as a Python library, and I didn't want to use recurrent or convolutional neural networks, which are a lot more advanced and take into account the temporal changes, especially I think the recurrent ones are good for the sequential inputs and time series that we would like to model our spins as. I try to fake it using this multi-layered perceptron and the thing simple with the scikit-learn. And instead of providing it to 1 spin, we provided 3 previous spins and tried to guess the 4th one. So it was just like faking this temporal effect by providing not 1 spin and not 3 inputs, but 9 inputs, and also connecting them. So we from our data derive a pairs of 3 spins and try to guess the 4th one. That way trying to model a more complex relationship.
And we can see here the code for it. It is also writing in a file that is already created. It was created at the same time when I ran the program. I created the pairs of 3. I was training them, splitting them, and also disabling shuffle. We are storing the accuracy, testing the results on the last 100 inputs. And we have a budget and also the same betting strategy. And you can see that the neural network achieved an even worse accuracy. Here we have now 9 symbols, which are 3 previous spins, and they are moving to the left sequentially. So the first 3 spins, then the next 3 spins starting from the second one. Here is the second one, now it is the first one, and so on. And it is trying to predict the next one, which in each case becomes the last one inserted from the right. And what is quite interesting about this approach in particular is that you can see it started losing money. And this is the turning point. A very similar input happened before. It was associating this input, like the similar one from the training data, with the win. And it was pretty confident indeed. But the actual outcome was loss. And we lost $10 from our budget. And let's see if it made any other mistakes. Yeah, it lost even more money. And some of the times, here this could have been mitigated with using a more smart betting strategy and just doing the bets when we are 80% or more confident it is going to be a win. But you can see this prediction right here, it was 95% sure. And I allowed it many iterations to try and to optimize the result. And it truly associates this sequence with a win in the next iteration. And you can see this is the next iteration. It is complete and utter nonsense. It doesn't even have two similar symbols. So in the end, our neural network lost $30, which is still a lot better than what I did, since it also was gambling a lot more carefully and thinking thoroughly when to try and bet and when not. But we can now kind of see an interesting convergence of how it tries to represent a pattern as something that would lead to results, when in reality the nature of the random number generators is that they are almost impossible to predict. And even though we used just 3 previous spins, we can kind of think our way through why this wouldn't work, even if I use more advanced techniques, such as recurrent neural networks, convolutional neural networks, and even transformers. And we arrive at the conclusion that the previous spins, almost no matter the number of them we take into account, so a human could, for example, try to guess from 5 previous spins at most. I don't think you could even try and check in a realistic number of times, even if you wrote down all the results from the previous spins you've got. But in a slot machine, this is the only data we get. We don't have any other data to work on except the symbols we get from the previous spins. Some other betting games and gambling games in general, especially the ones where the humans are involved, may take some kind of skill. But here, the house seems to always win. Somewhere around here, 3/4 of the way through, our neural network started developing the midlife crisis and its budget started tanking down. So in the end, what can we learn from these 2 machine learning models? Well, the simple and kind of naive logistic regression tells an interesting story that in the systems that seem rigged against you, sometimes the only winning move is to not play at all. This model, without emotions, decided to not gamble its money at all. And what is particularly interesting is that our more advanced neural network, for this very reason of trying to model more advanced patterns, started seeing patterns that were not real. The previous spins and the data we get from them is not nearly sufficient to model this complex behavior of random number generators. Also an interesting convergence to how this machine learning algorithm, inspired by the neurological human way of thinking, was also susceptible to the same bias. It started thinking that just because something happened before, it would also happen the next time. Just like the guy who once won betting red on the roulette and now thinks he's going to win every single time he plays. So our neural network started overfitting on the data, and it was almost sure if a certain pattern was leading to a win a previous time, it would also lead to a win this very time. So the correlation wasn't real and it started overfitting on the noise. So we come at a conclusion that these gambling systems are kind of designed to exploit the beliefs in patterns of ourselves and even machines where there are none and where they don't even exist. Our simple neural network was, and its implementation was not perfect, I can tell you right now, felt susceptible to the gambler's fallacy. It fooled itself, almost like a gambler would. I would quote Richard Feynman, who's one of my idols, because I think it's appropriate right here. And he said that the first rule is not to fool yourself, and you are the easiest person to fool. Then I did some background checking and research if extremely large neural networks, transformers, and modern AI systems could indeed try and break encrypted random number generators if they didn't know their implementation beforehand. And even if you created a neural network with the amount of inputs similar to the number of atoms in the universe, although it would be an interesting experiment, it couldn't really predict and model these patterns accurately, since the periods or the times
in which these randomly generated numbers happen in modern RNG systems are so large from the outside perspective. Even if you were watching for 1 billion years, you couldn't find a pattern that would lead to the sequence happening over and over again. And even with the advancement of quantum algorithms, because of their advanced parallelism, could, in theory, reduce the complexity of breaking it by a lot. It's still such a huge number and such a huge problem to do that in reality it would be impossible even then. So the reverse engineering in this kind of way is almost completely impossible, it seems to me. Of course, you can prove me wrong. I would be more than interested if you guys have anything to add or to correct what I said and even my code behind me. I also ran one simple test where I included the same input for the neural network in the training set and in the testing set, and it accurately predicted that that is the one that leads to the win, which means our neural network is working and it is detecting patterns that lead to wins, but the patterns don't exist, at least when realistically looking at the possible number of input data and previous spins we can account. So in the end, what we can learn from the simple logistic regression is that sometimes the best strategy is not to play at all. What we learn from the neural networks is that we are all susceptible to the biases and overfitting our assumptions of the past and projecting it to the results and future results. And that even quantum computers and large models would ask for a vacation if they were working on this problem for a long enough time. So it's best to leave them busy breaking the RSA. One last remark is that after this experiment, I trust my toaster more than these AI systems to break the casinos and gambling games. And I hope you learned something from it and that you won't bet your wallet on hope, because the house always wins, unless you are a Rain Man. See you in the next one.